Hello students, good evening. Welcome to today's Crux Conclusion Synopsis Classes of Fluid Mechanics. This is Sekar from Msigma Gokulam. In the yesterday's class, I have been discussing about the kinematics of the fluid flow. I also said that time that majority of the questions asked in FM in both civil and mechanical branches majorly will come from the kinematics of the fluid flow. In that kinematics of the fluid flow, I have described about the varieties of the fluid flows like steady, unsteady, uniform, non-uniform, compressible, incompressible, rotational, irrotational, etc. I have classified the flows and also I have defined the stream function, velocity potential, streamline, path line, streak line, and also I had given the conservation of mass or the continuity equation both in the finite form and also in the differential form. Okay. In fact, continuity equation is the law of conservation of mass, which says that mass can neither be created nor destroyed, but that could be given in two different ways. Continuity equation can be given in two different ways. One is in the finite form, that is, for the steady flow, mass flow rate is equal to rho AV is equal to constant. That is one. In the differential form, for the three-dimensional steady flow, it could be given as divergent V is equal to 0. That is dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Okay, where u, v and w, because continuity equation format is very famous format. Dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. For a steady three-dimensional incompressible flow, this is the format of the continuity equation which can be written as divergent v is equal to 0. Okay, where u, v, w are the three mutually perpendicular components of the velocity vector. Okay, u, v, w are the three mutually perpendicular components, right? Now, in fact, this could also be written as mass flow rate is equal to rho AV is equal to constant. If the fluid is incompressible, rho will be automatically constant. For an incompressible fluid, rho is density is independent of the pressure. All the liquids by default are incompressible. In fact, in most of the fluid mechanics problems, even many times, even the gas flows also we treat them as incompressible. I told you the criteria also. As long as the Mach number of the flow is less than 0.3, that compressibility effects can be neglected. We can treat the flow as incompressible as long as the Mach number is less than 0.3. Even for the gas flows, right? So if the rho is treated as constant, if the flow is incompressible, then the AV will be constant. What is that AV? The discharge or the volume flow rate, meter cube per second, right? This is the constant. Q is a symbol, we always use it for the measuring discharge. In fact, that is measured by using the venturimeter or the orifice meter, which are the flow measuring devices meant for measuring the discharge. Now let me give the actually yesterday I was have defined the velocity potential function phi and stream function psi. Okay, and I said equipotential line and constant stream function line are orthogonal to each other because they cut orthogonally, that is at 90 degrees everywhere in the flow field except at the stagnation points. I also said that equipotential lines and constant stream function lines. What do you mean by equipotential line? For any curve, if the phi value is a constant at every location on that curve can be treated as equipotential line. I had given the slope of the equipotential line also. And I had also given the slope of the constant stream function line. This is called as the stream function. Constant stream function line is nothing but a streamline. This is the velocity potential. Velocity potential. Both are scalar functions. Both are the functions of space and time, but generally the stream function will be defined for the two-dimensional flows. Okay, and I also said that the slopes of the equipotential line, the product of the slopes of the equipotential line and constant stream function line, if you just take them, it will be -1. That means they cut orthogonally. Equipotential lines and constant stream function lines cut orthogonally everywhere in the flow field except at the stagnation points, right? Now, the most of the questions that are asked in the gate is majority, particularly in the kinematics, they will be asking about the condition for irrotationality of a flow. I already said yesterday's class, irrotational flow is something like an idealized flow, inviscid flow. If you neglect the viscous influence of the fluid, we can treat the flow as irrotational. What do you mean by irrotational flow? The fluid particles simply translates from one location to the another location without any rotation about their mass centers. In case if there is a rotation component arising about any axis, about either x-axis, y-axis or z-axis, that flow could be called as a rotational flow. In fact, the rotation of the fluid element about any axis, maybe about x or maybe about y or maybe about z, x, y, z are the three mutually perpendicular coordinate axes, okay, in the space. Okay, if the rotation component arises either about x or either about y, either about z, and that flow could be called as a rotational flow. So, for a flow to be irrotational, all the three rotation components about all the three axes must become 0. So, if a fluid flow, a three-dimensional, fluid flow can be treated as irrotational. These questions were very commonly asked. Can be treated as irrotational flow only if all the three rotation components, of fluid about x, y and z axis only if all the three rotation components of fluid about x, y and z axis become 0. If this is x, this is y, this is z axis, this is the omega x, this will be the omega y rotation components, this will be the omega z. Only when all the three rotation components, say for example omega z, for a fluid element, for two-dimensional flow, it is just sufficient to calculate the rotation component about the z axis. For a two-dimensional flow in the xy plane, it is just sufficient to check for the rotation component about the z axis. Rotation component of fluid about z axis given by half into dou v by dou x minus dou u by dou y. This is the rotation, units are radians per second, and this is the rotation component of the fluid about z axis. Similarly, rotation component of fluid about y axis, it is the half into about the y axis dou u by dou z minus dou w by dou x. Omega x, rotation component of fluid about x axis. First of all, why these rotation components are arising, I already said. The main reason behind these rotation components to arise during the flow will be the viscous nature of the fluid. So I can say if the viscous effects are negligibly small, if you think that the flow is ideal or inviscid or non-viscous or inviscid flow or idealized flow, if you assume, then the flow will be automatically irrotational. Rotation components will not arise. About the x-axis will be, about this x-axis will be dou w by dou y minus dou v by dou z. So only when all the three rotation components become 0, that is, if omega x is equal to omega y is equal to omega z is equal to 0, then only three-dimensional flow will be irrotational. Three-dimensional flow will be irrotational. But generally, if the flow is two-dimensional, if the flow is two-dimensional in xy plane, but if the flow is two-dimensional in xy plane, it would be sufficient to prove omega z is equal to 0 to call the flow as irrotational. That means if the flow is two-dimensional in xy plane, if you prove that omega z is equal to 0, automatically the flow can be branded as irrotational flow. The flow can be branded as irrotational. That is, what is omega z? That means half into dou v by dou z, dou v by dou x minus dou u by dou y. It is just sufficient. If you just take this as 0, if you prove this as 0, automatically the flow will be irrotational, two-dimensional flow. So we have to thoroughly understand, to answer the questions of all the questions about the kinematics of fluid flow, we have to thoroughly understand what is the streamline, what is the velocity potential, what is the stream function. There is another rule also. Also that to call a fluid flow as irrotational, it is sufficient to prove del square phi is equal to 0, where phi is the velocity potential function, that is dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square is equal to, if we just prove that Laplace equation in phi as 0, then again the flow can be thought of as a velocity potential. If the flow can be thought of as a irrotation, that means if the phi is the velocity potential, if you prove that del square phi is equal to 0, that is this equation, again the flow can be treated as irrotational. And incidentally, when the flow is irrotational, del square psi is also equal to 0, where psi is the stream function. Incidentally, even when if the Laplace equation satisfies the stream function, that time also the flow can be branded as irrotational. So there are many ways of proving a fluid flow as irrotational. Now with this background, I shall solve some of the important questions that are given in the kinematics of the fluid flow, which are given in the previous gate questions or previous engineering services. See, whenever you are planning to prepare for a all India examination like a gate, where the lakhs of people will be writing the examination, that is conducted by the prestigious IITs, age-old IITs, and one must practice a good number of problems. So where do you get those problems? Means I suggest to solve all the previous year's gates. There are 30 years of gate papers, because gate papers are available outside since 1987. The first gate paper came out in 1987. So since 1987, you have got the papers available outside in the market, are available in the internet. Try to solve all the years of the gate papers, number one. After finishing that, if the time is permitting, also solve the previous engineering services papers, particularly IES prelims papers we can solve, because they will be relatively easy, much easier than the gate question papers. And if the time permits, you may try the ISRO papers, previous ISRO papers, previous DRDO papers, previous ISRO papers, or the BARC papers. They are all available, many questions are available in the net, but try to get a genuine paper, original paper. And we have got a last 10 years of ISRO papers. And my video is also there in ISRO latest recent examination. I had provided the solution also in the Msigma Gokulam app. You may see that ISRO paper also. I had given the key and explanation also. So that is how we can plan for as you practice more and more problems, the time taken by the students in the actual gate examination will become lesser and lesser. So I already said time management is a prime thing. Whenever you are facing the gate examination, how quickly, how accurately, there are two things, quickness and accuracy, both will matter. So you cannot sacrifice the accuracy just for the sake of solving the problem quickly. At the same time, to get the more accuracy, we can't spend too much of time on a given question, because 65 questions, 3 hours, 100 marks. So that is how the competition runs. So when you want to be in the race, and hit the correct answer, you must be practicing the more and more problems before attempting the actual examination. Like this, the velocity components in xy direction, that is a two-dimensional. Whenever you are given u and v, means it is clearly a 2D flow, because there is no mention of the w. Okay. Mostly the questions will be given 2D only. The value of lambda for a possible flow field involving incompressible fluid. Incompressible fluid means what? Incompressible fluid means density is constant. That is the meaning of this incompressible. Okay. When a possible flow field is there, it must satisfy the continuity equation. If your continuity equation is satisfied, it means that yes, there is a possibility of a fluid flow. So I will just make use of the continuity equation in a two-dimensional form. Continuity equation in a 2D form. Dou u by dou x plus dou v, because there is a possible flow existing there. Now dou by dou x of, what is the u there? Lambda x y cube minus x square y plus dou by dou y. Sorry, there is a small mistake I have done. It is a dou by dou y. Dou by dou y of, all they are partial derivatives. When I write dou, means dou is a partial derivative, d is a total derivative. So when you are differentiating with respect to y, we have to treat x as a constant. When you are differentiating with respect to x, treat the y as a constant. Partial derivative, no? Dou by dou y of xy square minus 3 by 4 y to the power of 4 is equal to 0. Implies, if you differentiate with respect to x there, it will become lambda y cube minus 2xy plus dou by dou y of xy square, that is 2xy. We have to treat the x as a constant, minus 3 by 4 into 4y cube is equal to 0. You will easily get the answer for the lambda in one of the options. Okay, can you easily get the answer for the lambda. For an incompressible flow field V, which of the following conditions must be satisfied? For the incompressible fluid divergent V bar is, this is a curl, this is a divergent. Okay, this is the equation for the continuity equation for three-dimensional steady incompressible flow. That is dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Answer is A, because he is asking the continuity equation satisfaction. A flow field which has only convective acceleration is. What do you mean by convective acceleration? Because yesterday I said already, acceleration arises whenever the velocity changes, right? When you talk about the acceleration, there are two things that would come into picture. One is called convective acceleration and other thing is called as a local acceleration. I would like to distinguish between these two. An acceleration A will have two components. One is called convective acceleration and other is called as the local acceleration. Convective acceleration that will arise due to change in velocity component, maybe u, v or w, change in velocity component that will arise due to change in velocity component from one location to another location. From one location to another location at a given instant of time. At a given instant of time. At a given instant of time, if the velocity component along any direction, maybe u, maybe along xy direction or a y direction or z direction, because velocity has three components along x, y and z, u, v and w. Any of these components, maybe u, v or w, will be different at different locations. At you got one value of u here, you have got a different value of u here. That means, yes, there is a convective acceleration. Or you have a different value of v here, you have a different value of v here. Yes, there is a convective acceleration in the y direction. So, if there is a change in velocity from one location to the another location, from one space, one point in the space to another point, at a given instant of time, that will arise the convective acceleration. Usually, best example for the convective acceleration is flow in a nozzle. Definitely flow in a nozzle definitely will have a convective acceleration because the velocity here and the velocity here will be different. Flow in a nozzle or a flow in a diffuser or a varying area duct. Yes, there will be a convective acceleration. What do you mean by local acceleration? The change in velocity may be magnitude or direction, because velocity has two modules. One is direction and other is magnitude. Any one of them changes, I say that the velocity is changing. Velocity has two distinct modules, magnitude, direction. If the direction constant, magnitude changes, I say that velocity is changing. If the magnitude constant and direction is changing, I say that the velocity is changing. So either one of them is changing, I say that velocity is changing. So at a particular location, if there is a change in velocity at a particular spot or location, with respect to time, then I say that there is a local acceleration. Okay. And in steady flow, mind that local acceleration along any direction is 0. In steady flow, local acceleration along any direction is 0. In uniform flow, the convective acceleration along any direction is 0. Mind that. Once again I repeat, in steady flow, what do you mean by steady? Things will not change with respect to time. In steady flow, the local acceleration along any direction, maybe x, y or z, it will be 0. In uniform flow, the convective acceleration along any direction will be 0. Yes, a flow field which has only convective acceleration is asking, non-uniform, in non-uniform flow it should be. Answer is A, steady. Answer is C. In steady flow, local acceleration is 0, but convective acceleration is not equal to 0. Is not equal to 0. Answer is C. Steady flow, local acceleration, but he has said only convective acceleration. See, in unsteady uniform flow, here there will be local acceleration, but the convective acceleration is 0. In uniform flow, convective acceleration is 0. In unsteady flow, local acceleration will not be 0. Local acceleration will be there because things will change with the time. Unsteady means if the parameters change with respect to time, time dependence will be there. Now one velocity component value, after a few seconds of time, there will be different velocity components. Okay. Answer is C. Consider two-dimensional velocity field. Usually I mentioned already, majority of the gate questions and will be asked about the two-dimensional flows. U is given, V is given. So this will be the U. This will be the V. Because any velocity vector in two-dimensional flow, it is written as U I bar plus V j bar, where I bar, j bar are the unit vectors along x and y directions. U and V are the components of the velocity vector along x and y directions. Now, we know the U, this is all U, that is V. Which of the following conditions needs to be satisfied for the flow to be incompressible? That means a two-dimensional flow is existing. We have to check whether the continuity equation is satisfied or not. That means dou u by dou x plus dou v by dou y is equal to, since flow is existing, continuity equation must be satisfied. Continuity equation must be satisfied. Right? You know the U, you know the V there. Implies dou by dou x of 5 plus a1x plus b1y dou by dou y of 4 plus a2x plus b2y should be equal to 0, because the flow is existing, your continuity equation in two-dimensional flow must be satisfied. Implies we are differentiating with respect to x. a1, this is a x, b1y, it is a, y is treated as a constant, b1 is also a 0, so that will vanish, this will vanish, plus dou by dou y, this is constant 0, this is 0, plus a1 plus b2 is equal to 0. Answer will be B. B is the answer. When you are differentiating with respect to x, treat y as a constant. When you are differentiating with respect to y, treat x as a constant, because it is a partial derivative. A channel of width 450 mm branches into two sub-channels having width 300 and this is 200. If the volumetric flow rate taking unit depth, this depth will be 1. The depth of the channels perpendicular to the plane of the figure is 1. You see that. Unit depth of an incompressible flow through the main channel is 0.9. Here flow rate is given. And the velocity in the sub-channel of width, here it is 3 meters per second. And what is the velocity in the sub-channel of here? Here what is the velocity is asking. Here what is the velocity? He has given this velocity, that is 3. Just write the continuity equation, because flow is existing, continuity equation must be satisfied. Law of conservation of mass. Density is a constant. Law of conservation of mass or continuity equation. Density being constant, mass flow rate is constant, right? Mass m dot in should be equal to the m dot out. This is m dot in. This is m dot in. This is m dot out. There are two outgoing flows. So the rate of mass flow entering should be equal to the total rate of mass flow leaving. But now because density being constant, it can be rated as a q dot, discharge in should be equal to the total discharge out. What is discharge in? He has given the discharge means flow rate. Discharge means flow rate. What is discharge out here? For the discharge out, I already said what is the formula for the discharge? Q is equal to area of flow into velocity. That is the formula for the discharge. Remember, this is the formula for the discharge or the volume flow rate will be area of flow into velocity. Here the velocity we don't know, but this area of flow we know. What is the area of flow? This width 300, this width 300, this is 300, right? Into 1. 300 means 0.3. 0.3 into 1, that is the area of flow into velocity, plus here this width will be, this width is given as this one. This is the width given as 200, that is 0.2 into 1, because when the flow is happening like this, area of flow will be this width into this one, because always whenever you talk about the discharge, area of flow into velocity, this area of flow must be perpendicular to the direction of velocity. If this is the direction of velocity, this will be the area of flow. What is the area of flow? This dimension into unit width 1, that is, right? 0.2 into 1 into what is the velocity? 0.2 into 1 into what is the velocity as given? 3. So now we will get the velocity V. Here in this channel, what is this velocity V is given by here, can be calculated. Mind that I want to highlight one important point here. Whenever we are calculating the discharge from the formula area into velocity, area of flow into velocity, area of flow and the velocity of flow must be perpendicular. If this is the velocity of flow, what is the area of flow? This is the area of flow. Width into this one. Here what is the area of flow? This width into 1. Depth of this figure perpendicular to the plane of the figure is 1. He has given unit depth. Streamline, path line, streak line are identical when the flow is steady. When the flow is steady. In unsteady flow, streamlines, path lines, streak lines all are different. In steady flow, all are identical. Flow is steady. Answer is A. I defined the 3 lines as steady: streamline, path line and streak line. Please go through all the videos, lectures I had given in our Msigma Gokulam map. I had covered about 50 to 60 hours of fluid mechanics classes, including machining, fluid machinery, hydraulic machinery, which is there in our Msigma Gokulam map. Please go through those classes before attending these Crux Conclusion and Synopsis classes, because the idea of providing these Crux classes is to quickly revise and to quickly put all the concepts in order in a structured manner, so that you would be able to answer the question at the fastest manner in the final gate examination. So that is the main objective. Objective of this particular Crux classes will be to inculcate, to imbibe the most fundamental concept in a very quick manner, in a sequential manner, so that using those concepts, student must be able to very fastly can attempt the question and come out with the most accurate and exact answer in the GATE examination. Consider the following: the components of velocity u and v along x and y directions in a two-dimensional flow of an incompressible fluid are given. U and v are given. There are totally 4 different flows there. 4 different flows: 1, 2, 3 and 4. Which of these will satisfy the continuity equation? Very simple question. Continuity equation in two-dimensional flow incompressible flow. Incompressible flow means density is independent of pressure. Dou u by dou x plus dou v by dou y is equal to, just check that which one will satisfy that. First, for example, I take the second flow, this one, dou by dou x of u, x plus 2 plus dou by dou y of v, 1 minus y. Is it equal to 0? Let's check. Dou by dou x of x means this is 1. Here dou by dou x of 2 is 0 plus here dou by dou y of 1 is 0 minus 1, 1 plus of minus. Yes, 2 is the correct. 2 is the flow 2 is the satisfies the continuity equation. And similarly, you may check with the third flow. Dou by dou x of x y t plus dou by dou y is unsteady flow. T is there means it is an unsteady flow. Clearly it is an unsteady flow. Okay, it should be an unsteady flow. X cube minus y square t by 2. Because if time parameters are existing only in the third flow, there is a time parameter. Definitely it will be, because as the time changes, things will change. Therefore, only this is unsteady flow. For unsteady flow, we have to take the dou rho by dou t also, right? Dou rho by dou t also we have to take. But let me check this. Is equal to incompressible. So density can be treated as a constant. Incompressible means density is practically a constant. X y t, that means yt plus dou by dou y, this is 0 minus 2y t by 2. 2 gets cancelled, so it is 0. Yes, this is again 3 is also satisfying. 2 is satisfying, 3 is satisfying. And if you just look, similarly you can check for the 2 and 3 are satisfying definitely, and the first one will be, if you just look at this, dou u by dou x, that is 2x into cos y, I am just taking minus plus dou v by dou y, that is minus 2x into sin y will be cos y. 2x cos y minus come out 2x cos, it will be 0. Yes, the 1 is also satisfying, 2 is satisfying, 3 is satisfying. So 3 are satisfying, and look at the fourth one. Look at the fourth one for the continuity equation satisfaction. That is here dou u by dou x, that will become this formula I am just checking. Log x will be 1 by x plus y. You treat y as a constant, dou u by dou x, and that is 0. And here it comes v, dou v by dou y plus x minus 1 by x plus minus 1 by x into 1 by x. We are treating with respect to the y as minus 1 by x. This will be, it will not be 0. So only 2, 3, 4. Sorry, 1, 2, 3. 1, 2, 3 are the correct answer. Answer is only these 3 are satisfying. Fourth one is not satisfying. See that log x is 1 by x. Differential of y will be 0 because you are differentiating with respect to x. And xy will be differential of y, we are differentiating. Therefore, it becomes x minus 1 by x. We are differentiating with respect to y. That is not equal to 0. So, fourth flow is not satisfying. Answer is 1, 2, 3. The streamline equation passing through the point 2, 3 will be the two-dimensional flow is given by, we have to calculate the equation of the streamline. It is a very commonly asked question in GATE. Many times, so many times this kind of questions were asked in GATE. U is A, V is A. What is the equation of streamline? First of all, differential equation of streamline will be dx by u. How did I define the streamline? Streamline is an imaginary curve drawn in the fluid flow regime in such a way that if we just draw the tangent to the curve at any location, it will give the direction of the velocity vector. Streamline is an imaginary curve drawn in the flow regime in such a way that if you draw the tangent to the streamline at any point, that will indicate the direction of the velocity vector at that point. If you draw the tangent at any point, that is indicating the direction of the velocity vector of the fluid at that point. That means it has two components, one is v and other is u. So if this is tan theta, if you just take the slope of that streamline on xy plane, it will become v by u. That will result in dx by u is equal to dy by v. Okay. What is that? Dx by u is a, dy by v is also a. They get cancelled. If you integrating x is equal to y plus constant of integration. But he has given the put x is equal to 2 and y is equal to 3 to get the constant of integration. Implies 2 is equal to 3 plus c. C will be 2 minus 3, that is minus 1. So x will be y minus 1. X plus 1 is equal to y. This is the equation. B is the answer. Slope of the streamline will be tan theta dy by dx. It will be v by u. So x plus 1 is y. That is the equation of the streamline. A two-dimensional flow field is defined as u I bar plus v j bar. If you compare this equation with that, u will be x, v will be minus y. Two-dimensional flow field, the equation of the streamline passing through the point 1, 1. What is the equation of the streamline? Dx by u is equal to dy by v for streamline. Differential equation of the streamline implies dx by u is x, dy by v will be minus y. Integrating log x, this minus 1 taken, it is a log y, it is log y. When you take the minus to the, because log x to the power of n is n log x, minus 1 taken log y, that means minus will go to the middle, log 1 by y plus constant, right, implies log x minus log 1 by y, it is another constant we can write, log a minus log b. Log a minus log b is log a by b, ln log a by b, 1 by y, implies log y, log xy is equal to log constant, if we take the anti-log, xy is equal to constant. Put x is equal to 1, y is equal to 1, implies xy, c will be 1. So, xy is equal to xy is equal to 1, xy minus 1 is equal to 0. Answer is A. A is answer. Okay. Log A minus log B is log A by B. So, if you take the anti-log, xy will become constant. Put x is equal to 1, y is equal to 1, c will be 1. So, xy is equal to 1, xy minus 1 is equal to 0. That is the equation of the streamline. State whether the following is physically possible. Yes, for any flow to be physically possible, if you want to prove that a given fluid flow is physically possible, just check that whether it satisfies the continuity equation. It is a two-dimensional flow. Just check this equation. Dou u by dou x plus dou v by dou y is equal to 0. Dou by dou x of u is 3xy square plus 2x plus y square plus dou v by dou y of v. V will be x square minus 2y minus y cube. Whether it is equal to, if it is equal to 0, possible. If it is not 0, not possible. Okay. It is a clearly, it is a incompressible flow because no density doesn't, because in the incompressible flow density is practically a constant. It is a steady. Why it is steady? It does not containing any time. See, no t parameter, no t. That means definitely it should be it will be a steady flow. If t is there in the function, it will be unsteady. I think this will become 0 only. Let's just check dou by dou x means 3y square plus 2 plus 0 plus dou by dou y, this is 0 minus 2 minus 3y square minus 3y square minus 3y square minus 2, it is 0. Yes, it is a possible steady incompressible flow. Answer is A. Answer is A. Possible steady incompressible flow. Because that continuity equation is satisfied. This continuity equation satisfied, it will be definitely a possible case of steady incompressible. So this is a simple matter of the continuity equation. He is asking flow system with flow directions. There is flows are entering, two flows are leaving. Velocities of the corresponding needs, velocity of the V2 will be. Areas are given. So conservation of mass must be satisfied because the flow is steady. M dot in should be equal to the M dot out. What is M dot in? A1 V1 plus A2 V2, that is entering, right? This is entering, this is also entering. Should be equal to the A3 V3 plus A4 V4. You will directly get the velocity V2. All the areas are given, we just substitute there. All the areas, all the velocities are only one unknown. V2 is not there. You can easily get the V2. There are two masses entering. This is entering, this is entering. This is leaving, this is leaving. So for the control volume, the rate of the mass entering should be equal to the rate of the mass leaving. That is called law of conservation of mass. Mass can neither be created nor destroyed. It is also similar things there. He has asked pipe labeled as A. Here the velocity, here this velocity is asking. The pipe cross sections are shown in the figure, the velocity in the pipe labeled as A. It is 6 liters, 5 liter, 5 plus 2, 5, this is going out, this is coming in. 6 plus 5, 11, 9 plus 2, 11, satisfied. See, this is entering, 5 is entering, 6 is entering, 5 plus 6, 11. What is going out? 9 is going out, 2 is going out, 9 plus 2, 11. So, continuity equation automatically gets satisfied. He is asking the velocity. Discharge is equal to area into velocity. Discharge is 6 liters per second is equal to area, I don't know, velocity. Area is been given there, sorry, area is given 40 centimeters square, but this is given in liters there. So, let us check 6 divided by 1000. 1000 liters is, you have to check the one correct units there. 6 divided by 1000 meter cube per second. Area should be written in meter square. 40 into centimeter square, no, 1 by 100, 10 power minus 4 into velocity. You will get the velocity in meters per second. I have converted the discharge into the meter cube per second. Area is 40 centimeter square, 40 into 10 power minus 4. If you write the area, you write in meter square, velocity you write in meters per second, so that you will get the meter cube per second. 1000 liters is 1 meter cube. You will get one of those answers. It is also simple question. If the in the below layout, what is the velocity in 200 mm here? Here this velocity is asking. This velocity is asking. So there is a mass entering here. There is a mass leaving. There is a mass leaving. Flow is steady. When the flow is steady, m dot in should be equal to the m dot out. Flow is steady. That is, the rate of mass entering should be equal to the rate of mass leaving. So, pi by 4 d square, pi by 4 d1 square into v1, that is area into velocity, should be equal to the pi by 4 d2 square into velocity v2 plus pi by 4 d3 square into velocity v. This has been given, v1 given, this given, only we have to calculate this. Everything pi by 4 gets cancelled here. No, you just substitute all the diameters and velocities, you will get the velocity v. You will get the velocity, this velocity. This is the velocity, unknown velocity in the third pipe. Area of flow into velocity, that you will give the discharge. Because density is constant, as long as the density is constant, mass flow rates are proportional to the volume flow rate. If rho is constant, that is flow is incompressible. If the flow is incompressible, that means density is practically a constant. Then the mass flow rate is directly proportional to the volume flow rate or discharge. Volume flow rate or discharge, as long as the density is constant. That is why in the continuity equation, whenever you are writing the continuity equation or conservation of mass, you may write as well in terms of the volume flow rates rather than the mass flow rates, because mass flow rates and volume flow rates are proportional because the density is constant. A two-dimensional flow field has been given, U is given, V is given. Mostly two-dimensional will be given. Sometimes W also may be there, but that is rare usually. Usually two-dimensional flows are commonly given in the gate. This is a previous gate question, where T is the time. It is an unsteady flow. T is appearing here. Time parameters are appearing means it is an unsteady flow. The equation of the streamline. We know that for streamline in the differential form, dx by u is equal to dy by v. What is u given? X square t. What is v given? Minus 2xyt. T gets cancelled. X also gets cancelled. It will become dx by x is equal to minus dy by 2y. Okay. Integrating log x is equal to minus half into log y plus some constant. Log x is equal to this minus half will go to that 1 by y to the power of half 1 by root y plus some other logarithm constant. You take it left side, log x minus log x minus log 1 by root y, log a by b. Okay, log a minus log b is log a by b. Log x divided by 1 by root y is equal to logarithm of a constant. If y will go x root y is constant if you take the anti-logs. Okay, x square y is equal to constant. Answer is A. A is the answer. If you take the anti-logs, you will get x root y is equal to constant, x square y is equal to constant after squaring. After this, you take the anti-log, you will get this equation. It is also similar question. Exit velocity in the pipe 3 is asking this velocity. Very simple question. This velocity is asking. Mass entering, mass leaving. You just write this A1 V1 plus A2 V2 is equal to A1 V1 m dot in is equal to m dot out. A1 V1 entering, this is entering, A2 V2 entering, this is leaving. A3 into, he has given the areas and velocities, just get the V3. This is a continuity equation, right, for steady flow. Just take 1 minute break. Hello students, welcome back to the class. I have done the fluid kinematics where we have talked about the motion of the fluid without bothering about the forces that cause the motion. The main difference between the kinematics and the dynamics is in the kinematics we will just describe the fluid flow without bothering, without concerning about the forces that cause the motion. Whereas now I am going to start the fluid dynamics, topic called fluid dynamics where I will consider the forces that are causing the motion. I will just identify, I will just probe, I will just identify what are all the various forces that are acting over a fluid element undergoing motion. Where a fluid element is undergoing motion, I will just identify all the forces acting on the fluid element, and then I will apply the most fundamental equation of mechanics, applied mechanics, called as the Newton's second law of motion, okay, or law of conservation of momentum. Because I already said yesterday, any fluid mechanics problem can be solved with three conservation rules. One is conservation of mass, which is continuity equation. Second thing is the conservation of energy or law of conservation of energy, which I am going to derive it here. And third thing is called as the conservation of linear momentum, also known as the impulse momentum equation. Three conservation rules: conservation of mass, conservation of energy, and conservation of linear momentum, also called as the impulse momentum theorem or impulse momentum equation. And conservation of mass, we have done it very extensively in the previous. Now I will identify the forces there. So whenever a fluid element is undergoing motion, whenever a fluid element is undergoing motion, various forces that will be asking are gravity. Main in the order of priority I am writing: gravity, weight of the element. Weight will always be there. Every fluid element has got some mass, therefore it is subjected to the weight because of the gravitational field, that is mg. And then pressure forces, P for the pressure forces. Pressure forces always act normal to the area and onto the area. Any fluid pressure forces, suppose if we just consider a fluid element, undergoing motion, these are the direction of the pressure forces, act onto the area, perpendicular to the area, okay. If this is the direction of the pressure forces in the y direction, these are the direction of the pressure forces in the y direction, these are in the x direction. So pressure forces will always be normal forces acting onto the area, perpendicular to the area, normal, proportional to the area. Then is the viscous forces, which is a tangential force or a shear force, which will be always be there whenever a real fluid is undergoing motion. Whenever a real fluid means fluid having viscosity. Ideal fluid means fluid having zero viscosity. Whenever a real fluid is undergoing motion, there will always be a tangential forces or the shear forces acting parallel to the area. If the pressure forces are acting normal to the area, viscous forces will be acting parallel to the area. Right. If the fluid is element is undergoing motion like this, viscous forces will always act parallel to the area or the tangential to the area. They are proportional to the area, but they act along the area. Whereas the pressure forces are the normal forces which act perpendicular to the area. Please, I request all the students to come with the chart with me, because I am observing that there is a chart box. Any doubts if you are having, please post in the chat box. I will very much welcome your doubts, and I would be able to clear your doubts at instantaneously by looking into the chat box. Any students, please you can interact with me in the chat box. And then we have the gravity, pressure, viscous, and we have the turbulent forces, and we have the compressibility. See, for the compressibility, we will have the surface tension. So these are all the various forces acting on a fluid element undergoing motion. There are big list of gravity, pressure, viscous, turbulent forces. Turbulent forces are arising, turbulent forces will arise due to the intermixing, due to the intermingling among the fluid layers. Turbulent means intermingling or intermixing of the fluid masses are rather called as eddies. Eddies or turbulence both mean the same. So turbulent forces will come into picture only if there is too much of intermingling or eddies formed during the flow. And the compressibility force, these compressibility force will be significant only when the fluid flow motion is very rapid, very fast, very quick, okay, then only the compressibility effects will come into picture. And the lastly but not least, last one will be the surface tension, which is of very low magnitude. Among all the forces, surface tension forces are very low in magnitude, weak forces, weakest forces, which will be significant only when the depth of flow is very, very small. When the free surface having a very low depth of flow, then only surface tension forces will consider, otherwise we neglect. But most of the cases, turbulent force, compressibility force and surface tension forces are usually neglected. Most of the cases. I already said, when can you neglect the compressibility force? If the fluid density is practically a constant, if the fluid velocities are low, not very fast, particularly all the liquid flows, we may neglect the compressibility force. If there is not much mixing, we can neglect the turbulent force. If the depth of flow is significant, if the depth of flow is not small, then we may neglect the surface tension forces. Anyhow, surface tension forces are the weakest, are the very low magnitude forces as compared to the other. So if you neglect these three, the most significant force will be gravity, pressure and viscous. Okay. And of course, if you consider the turbulent, then if you write the net algebraic sum of all the forces acting on the fluid element will be the net algebraic sum of all the forces acting on the fluid element along the x direction must be equal to the rate of change of linear momentum of the element along the same direction. This is also called as the Newton's second law of motion. The net algebraic sum of all the forces. Force is a vector quantity having a direction and magnitude. The net we have to take the components of all the forces along the x direction, we have to add them up algebraically. Net algebraic sum of all the forces acting in the element along the x direction should be equal to the mass times acceleration of the element along the x. Then it becomes Fgx plus Fpx plus Fvx plus Ftx. I have neglected the compressibility and surface tension. This equation of motion is called as the Reynolds equation of motion. See, in the fluid dynamics, we will bringing the equations of motion, very fundamental in the fluid mechanics. After all, fluid mechanics is all about understanding the equation of motion and finding the solutions for them. Okay. And they are mathematical equations. Some are single order, some are second order equations, some are first order equations. Okay, some equations of motion are second order, some equations of motion are first order. So we have to formulate the differential equations, try to get the solutions, and by writing the boundary conditions, etc. So that is why to understand the fluid mechanics, fluid mechanics is basically a mathematical science. It is not developed over a year. It is developed over centuries. So all these fluid dynamics equations were developed over in 17th or 18th centuries as such. Okay, because this is the oldest science, fluid mechanics is. There are so many people who have contributed to the fluid mechanics because now it envelops so many branches of engineering. Okay, this is Reynolds equation of motion. Now if you neglect the turbulent forces, neglecting this is called as we are considering gravity, pressure and viscous. It is called as the Navier-Stokes equation of motion. It is also second order equation. Navier's very famous equation in FM. Navier-Stokes equation of motion, non-linear second order differential equation this is. Considering three varieties: gravity force, pressure force, viscous force. Therefore, we are talking about the viscous force, it is applicable for the real fluid also, because only real fluid will have the viscous nature. Then comes, if you think that viscous forces are negligibly small, that means if you neglect the viscous influence of the fluid, if you think that fluid as ideal or the flow as irrotational or inviscid fluid flow, if viscous forces are neglected, that is when fluid is ideal, that is when fluid flow is inviscid, or irrotational, when fluid flow is inviscid or irrotational, then only two forces, gravity and pressure, this is called as the Euler's equation of motion. In the Euler's equation of motion, we consider only pressure forces and gravity forces. We neglect the viscous force. Okay. Gravity and pressure. Now, it could be easily derived, the Euler's equation of motion, by taking a small if we just take the small streamline, a small cylindrical element glowing along the streamline, flowing along the streamline with a velocity v. Now, if we just draw the free body diagram for this cylindrical element of length ds and cross sectional area dA, okay, the various forces acting on this will be pressure force, third thing will be the gravity force. Gravity force will be mg. Okay. This is the ds is the differential length of the element and dA is the differential cross sectional area. This pressure force, if you just look at this, pressure force will be pressure into area. Here the pressure force will be, here if P is the pressure here, but then what is the pressure here? P plus dou P by dou S into ds, because rate of change of pressure with respect to the streamline, streamline length, into length of the streamline. This is the pressure acting here into area. This is the pressure force. What is M there? Rho into dA into ds. What is dA into ds? Volume of the element. Volume into density will give the mass. Mass into acceleration due to gravity. So this is the free body diagram by considering the free body diagram by considering the small differential cylindrical element of length ds and cross sectional area A. Please note that in the free body diagram of that differential fluid element, in that free body diagram, we consider only two kinds of forces. One is pressure force acting normal to the area and also the gravity force. No viscous forces are there. Flow is irrotational. Flow is steady, incompressible, irrotational flow. These are the assumptions for deriving the Euler's equation of motion. Steady flow, incompressible flow, irrotational flow. So, if you write the Newton's second law of motion, sigma Fs. All the forces acting should be mass into acceleration also in this direction. So, P into dA upward direction plus minus, because this is opposite, P plus dou P by dou S into dA ds into dA minus mg cos theta, because if you just take this as theta minus mg cos theta will be m into AS. So, this is the sigma Fs is equal to MAS, Newton's second law of motion along the streamline. Newton's second law. This acceleration AS, can be written as V into dou V by dou S plus dou V by dou T. But in a steady flow, dou V by dou T is 0, because flow is steady. Now, when the steady flow is happening, there is no change of velocity with respect to that time. So, acceleration is V into dou V by dou S, we can write. M is equal to density into volume, dA into ds. That is the mass of the element. Cos theta will be, if this height is taken as dz, cos theta will be adjacent side by hypotenuse, right? Cos theta will be dz by ds. Now, if you simplify all the parameters there, if you write that AS also there, you can easily get the Euler's equation of motion along this streamline, which can be written as dP by rho plus VdV plus GdZ is equal to 0. This is the Euler's equation of motion along a streamline for a steady incompressible or compressible also we could write incompressible or compressible, because rho is inside, right? When the rho is treated as constant, it will become the incompressible or compressible we can write, because incompressibility or compressible, where does it matter? If the density is a function of pressure, it is compressible. If density is not a function of pressure, if density is constant, it is incompressible. V is the velocity, G is the acceleration due to gravity, and Z is the elevation. This is the Z direction. dz, the change in elevation, Z direction, Z is the elevation. P is the pressure, rho is the density, V is the velocity. So, this is the Euler's equation along the streamline. Euler's equation of motion along streamline. Now, the same Euler's equation of motion we can write in terms of the along the x direction, along the y direction also. This is the streamline. See, the fluid element is moving along the streamline. This is the streamline. The velocity of the fluid element is along the streamline, right? And the same Euler's equation of motion I could write for the along the x direction and along for the y direction, like this. In the Cartesian x direction, Euler's equation of motion along the x direction, it could be written as x minus 1 by rho into dou p by dou x is Ax. What is that Ax? acceleration along the acceleration u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. Flow is steady, no time variation there. This is the Euler's equation of motion along the x direction, where x is the body force potential along the x direction. Body force potential along the x direction is capital X. This is the Euler's equation of motion along the x direction. Similarly, we could write along the y direction also. That is, this is the convective acceleration of the fluid along x. This is the convective acceleration. There is no local acceleration here because we are assuming the flow as steady, no? Steady flow. For steady flow, there is no local acceleration, only convective acceleration will be there. What is this x? Body force potential along the x direction. Similarly, in the y direction also we could write that is u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z. This is the convective acceleration along the x direction. This is the Euler's equation of motion along the y direction. Euler's equation of motion along y direction. See, basically Euler's equation of motion is a application of the Newton's second law of motion, which I have learnt in physics also. The net algebraic sum of all the forces acting on a fluid element along a given direction must be equal to the mass times acceleration of the element along the same direction. Newton's second law of motion is a vector equation. Net algebraic sum of all the forces along a given direction and the acceleration of the element along the same direction, they must be along the same. Actually, see, F is equal to ma. That F and A should be along the same direction. When you say F, it is a net algebraic sum of all the forces. What are the forces we have considered here? Gravity and pressure only. We didn't consider the viscosity for writing the Euler's equation. Why? In the Euler's equation of motion, we have assumed the fluid as inviscid and the flow as irrotational. Okay. If you consider the viscous force, then the equation of motion will be a second order equation. This is a first order equation. See, all these equations are first order equation. If you consider the viscous forces also, then that will become the Navier-Stokes equation of motion, which is a second order non-linear differential equation. This is a first order equation. The difference between the Euler's equation of motion and Navier-Stokes equation of motion is, in the Navier-Stokes equation of motion, we consider the viscous forces. In the Euler's equation of motion, we don't consider the viscous, only we consider pressure and gravity, assuming that the fluid is ideal, right? Now, we got the Euler's equation. So, now by integrating this Euler's equation of motion, we get the most important equation, the centralized concept of the fluid mechanics called as the Bernoulli's equation. Integration of Euler's equation of motion. Deep along the streamline, this is the Euler's equation of motion. P is the pressure, rho is the density, V is the velocity, and Z is the elevation measured with reference to some arbitrary datum. This is Euler's, right? by integrating integral dp by rho plus integral vdv plus integral gdz is equal to constant. But if rho is treated as a constant, because the flow is treated as incompressible, most of the occasions we treat the flow as incompressible only. But of course, there is a separate chapter called as the compressible flow, where the Mach number and density changes all must be accounted. That is a separate topic, I will deal it later. So if rho is constant, the fluid is incompressible. That is not, rho is not a function of pressure, it becomes P by rho plus V square by 2, G is anyhow a constant, Gz is equal to constant. If we just look at the each term here, here in this equation, P by rho, V square by 2, Gz, each term here will indicate the energy of the flowing fluid per unit mass. We all know in the physics also, kinetic energy for a flowing fluid will be half mv square. Kinetic energy is half mv square. Potential energy is mgz or mgh. Pressure energy will be PV, flow work. In the thermodynamics, it is also called as a flow energy or a flow work. PV, P into multiplied with specific volume. Specific volume is the reciprocal of the density, we all know that. Specific volume and density are reciprocals. So each term here will indicate, if we just look at this half mv square is the kinetic energy. Mgz is the potential energy, energy by virtue of the mass and its elevation. Okay. And P by rho is the pressure energy. Pressure energy we can call flow energy. Flow energy also they also called as a pressure. So each term pressure energy per unit mass. If you just put m is equal to 1, m is equal to 1, and this is a pressure energy per unit mass, P by rho. So this term will indicate the pressure energy per unit mass. This term will indicate the kinetic energy per unit mass. This term will indicate the potential energy. It's pressure energy, kinetic energy and potential energy. Of flowing fluid per unit mass in joule per kg. This is the pressure energy, this is the kinetic energy, this is the potential energy. Sorry. So that sum of these three energies is called as the total energy. Now I divide throughout with G. If we just divide throughout with G, it becomes P by rho G V square by 2G plus Z is equal to constant. Here rho G will be put, rho G is equal to W. What is the W? Very important property in fluid mechanics called as specific weight of fluid in kilonewton per meter cube. So if you write that, it will becomes P by W plus V square by 2Z plus Z is equal to constant. So, each term here will indicate the head. This is called as the pressure head. See, the head is a very commonly used term in FM. Head means energy. Head and energy are synonymous terms. Units are different. Energy of the flowing fluid per unit weight is called as the head. A fluid is flowing. A flowing fluid may possess three different kinds of energies. One is called pressure energy, kinetic energy and potential energy. This energy of the flowing fluid per unit weight, if you write, that corresponding term is called as the head, having the units of meter. This is called pressure head. This is called kinetic head or velocity head, both mean the same. Kinetic head they call, or velocity head, all mean the same. And this is called as the potential head or datum head. Datum head also this. So basically head means energy of flowing fluid per unit weight. Energy of the flowing fluid per unit weight. What are the units of that? In meter. Generally energy is, what are the energy units? We know from the physics, energy means units of Newton meter or joule. When you divide with energy by weight, if you write, weight is the force. Newton meter divided by Newton. Newton gets cancelled, you will get the units of meter. So energy per unit weight of the flowing fluid is called as the head. Pressure head, velocity head, potential head or datum head. So this is the equation called as the Bernoulli's equation. Therefore, according to this is called as a Bernoulli's theorem. Bernoulli's theorem. If there is no loss of head or energy, if there is no loss or head of energy of flowing fluid, the total head of the fluid that is P by W plus V square by 2G, the sum of the three heads is called as the total head. The total head of the fluid remains constant between any two locations in the fluid flow. Between any two locations in fluid flow. That is P1 by W V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2. If there is no loss of head between 1 and 2. 1 and 2 are any arbitrarily selected locations. Between location 1 and location 2, I say that there is no any loss of head or energy. First of all, why there is a loss of head or energy during the flow means there may be so many reasons. The main reason will be the head loss or energy loss due to friction. See, this Bernoulli's equation can be written between any two locations in the fluid flow, provided if there is no viscous effects considered. That is why when you talk about the boundary layer formation or a body, can you write the Bernoulli's equation inside the boundary layer? Means we cannot write, because in the boundary layer there will be viscous effects are definitely considered. Outside the boundary layer we can write between any two locations, because outside the boundary layer viscous influence is neglected, because boundary layer is a thin region which divides the flow into two domains. One is the flow in that within that boundary layer is viscous flow. Flow outside the boundary layer is inviscid flow or irrotational flow. In the irrotational flow we could write any between any two locations, but not within the within that boundary layer region, a thin region inside which viscous effects are very much predominant. Okay. So, Bernoulli's equation has got some limitations to write that. What are the limitations? Fluid is treated as inviscid or the flow is treated as irrotational. Okay. I will elaborate about this Bernoulli's equation after the break. Take 5 minutes break. Hello students, welcome back to the class. Bernoulli's theorem in a pictorial way I could write like this. Supposing if this is a fluid flow control volume or fluid flow regime, this is the section 1, this is section 2. The flow is happening like this. Here if the pressure is P1 here and the elevation is randomly selected. Z1 is the elevation. Here the Z2 is the elevation 2. Elevation means selected arbitrarily from some arbitrary datum. At the arbitrary datum, Z value is taken as 0. The flow is happening like this. So, if there is no loss of head, between 1 and 2, why there is a loss of head? First of all, I already said main loss because of the fluid friction, because of the friction against the flow. Frictional resistance is the prime reason behind the head loss. Okay. Then what may cause that frictional resistance means there are many reasons. Main reason is viscosity. The viscosity of the fluid itself may cause some frictional resistance against the flow, due to which some energy of the fluid may get converted into heat. So as the flow is happening, fluid will always suffer resistance against the flow. What will cause that resistance? The basic viscous nature of the fluid and also maybe the roughness of the pipe and also because of the turbulence. Many reasons will be there again because of why the frictional resistance will be there. Because of that frictional resistance, some of the fluid energy will get lost in overcoming that frictional resistance, and whatever the work done by the fluid in overcoming that frictional resistance gets converted into heat. So that is why in thermodynamics we will name that viscosity as some reason for the irreversibility, because any viscous flow will generate some entropy in the thermodynamic point of view, I can say. So as the flow is happening, there may be a frictional resistance. If you neglect the frictional resistance, if you think that the flow is idealized flow, and if there is no loss of head, it is P1 by W plus V1 square by 2G plus Z1 is equal to the total head at the section 2, V2 square by 2G, no loss of head. Supposing if there is loss of head between 1 and 2 due to friction, etc. Actually, there are many other reasons also there. Need not be only frictional resistance. Frictional resistance is the main reason behind the head loss. There are some other reasons also: sudden enlargement, sudden contraction, pipe bends, gradual contraction, gradual enlargement, pipe walls, pipe fittings. All these things also may contribute to some head loss or the energy loss. But the major head loss will be the head loss due to friction. We have got different equations for calculating that head loss due to friction. Hagen-Poiseuille equation, Darcy-Weisbach equation. There are varieties of equations are there. I will elaborate them how to calculate that head loss due to friction later. So, okay, different equations of in the fluid mechanics are available to calculate that head loss due to friction. Example, Hagen-Poiseuille equation. Another example is Darcy-Weisbach equation. Okay. Supposing if there is a head loss, between 1 and 2, then this is the total head minus head loss due to friction is equal to see, the total head of the fluid keeps decreasing in the direction of the flow. The total head of the fluid keeps decreasing in that direction. If the total head of the fluid is 100 here, between 1 and 2 it may lose a head of around 10 or 15 meters, 15 meters, and finally the energy at the exit may be around 80 units. See, the head loss will be contributed by frictional resistance or some other reasons, but definitely the total head of the fluid keeps decreasing in the direction of the flow. Okay, either it remains constant or decreases due to the frictional resistance against the flow. Okay, so this is how we can understand the Bernoulli's equation. This is a law of conservation of energy. Basically, Bernoulli's equation is the law of conservation of energy. Energy can neither be created nor destroyed. And there may be some devices, hydraulic devices, sometimes which may extract the energy from the fluid, like turbines. Sometimes there are the devices which will energize the fluid, which will supply the energy to the fluid in the form of, by example, a pump or a fan. Pump or a fan will give the energy to the fluid, whereas a turbine will extract the energy from the fluid. Okay. Now, if we just look at the basic applications of the Bernoulli's equation, best example is venturimeter. Venturimeter is a device to measure discharge or flow rate. In meter cube per second. The main purpose of using the venturimeter will be flow measuring device or the discharge measuring device. It is a converging pipe and followed by a lengthy diverging passage. This is the main pipeline. This is the inlet. This is the throat. This is the exit. Between inlet and the throat, there will be a U-tube manometer is connected. So, as the area decreases, velocity will increase. As the velocity increases, pressure will decrease. So, this is the manometric liquid levels. If X is the difference in manometric liquid, having the specific gravity of Sm, just need to note down the difference in the two limbs, difference in the manometric liquid levels in the two lift limb. This is a U-tube manometer connected between inlet and the throat. Throat is the minimum area of cross section. Generally, converging pipe will be short in length. This is the diverging passage will be longer to avoid the flow separation. The main reason why it is kept very longer is this angle should not be kept more than 10 degrees to avoid the flow separation here. Okay, the diverging passage is kept much longer in length as compared to the converging passage. So, this is the inlet, throat, exit. And this is a main pipeline where the fluid is coming. Fluid may be having a specific gravity, yes. This may be oil, this may be mercury, this may be air, this may be water. Any combination is possible. Some oil, some mercury, or sometimes air, gas and water. It could be anything. Right? Now, in fact, the discharge, what is the basic principle is, between 1 and 2, elevation is same, but the area is decreasing. Q is equal to A1 V1 is equal to A2 V2, right? But the area is decreasing, the velocity will be increasing, P1 by W plus V1 square by 2G. If you write this is a continuity equation. So the three equations will be used to get the discharge. One is continuity equation, second thing is the Bernoulli's equation, third thing is the manometric equation. By using the three equations, we can get the discharge. This is a continuity equation. A is the area, inlet area, V1 is the velocity, throat area, throat velocity. Neglecting loss of head between inlet and throat, there may be loss of head, but we neglect that. Same elevation, therefore Z will get cancelled. But V2 will be more than the V1 because A2 is lesser than A1. Therefore, V2 square minus V1 square by 2G is equal to P1 by W minus P2 by W. This is also called as the Venturi head. The difference of the pressure heads between 1 and 2, between inlet and the throat, that can be called as the Venturi head. If the pressure is P1 here and that V2 could be written as Q by pi by 4 d2 square throat diameter, and V1 will be Q divided by pi by 4 d1 square. Now, by substituting them, you will get the theoretical discharge as A1, Q by A1, no? This is Q by A1, this is Q by A2. Areas are, no? These are the A1, A2 are the areas there. A1, A2 root 2 GH divided by square root of A1 square minus A2 square. This is the formula for the theoretical discharge. Theoretical discharge, A1, A2 are the inlet area and throat area. This is a section 2. Inlet is the section 1. Then how to get that Venturi head? Venturi head is obtained from the manometric level difference, X. X is the difference in the manometric liquid levels in the left limb and right limb. So that H could be obtained as X into Sm by Es minus 1. So you can get the Sm is the manometric liquid specific gravity. S is the specific gravity of the flowing liquid. We can get the Venturi head and substitute here. We know the A1, A2, inlet area, throat area. We can get the theoretical discharge. But actual discharge will be slightly lesser than this theoretical discharge. That actual discharge will be coefficient of discharge into theoretical discharge to account for the losses, where the coefficient of discharge of the Venturi meter is in the order of 0.97 to 0.98. Mostly 0.98 they take. Coefficient of discharge. Why that coefficient of discharge is defined as the ratio between the actual discharge and the theoretical discharge. See, it will be around 0.98 or 0.97 we may consider for the Venturi meter. H is called Venturi head. This is how we will understand the Venturi meter to measure the discharge. Now I will give the second application in the form of the Pitot tube. Pitot tube is an instrument meant for the velocity, to measure the velocity of the flowing fluid. In fact, Pitot is the name of the person who has first used it to measure. Pitot has used this instrument to measure the velocity of the water flowing inside a river. Okay, Pitot is the name of the person. Venturi is also name of the person. Pitot first used this instrument to measure the velocity of the water coming in the flowing in the river. This Pitot tube basically comprises a L-shaped bent tube. Okay, when the water coming from the upstream, it has got some velocity v. When it enters the petard tube, which is facing this water coming from the upstream, there is a narrow hole. There is a narrow hole, a small tip that is when the water enters into the narrow hole, it will become the stagnant. That will become the water will become the stagnant at this tip, at the tip of the petard tube. The kinetic energy of the water will get converted into the pressure head. The water will rise in the petard tube, right? So this point 2 is known as the stagnation point. That means V2 is 0. So V1 could be, V1 is the velocity of the water coming from the upstream. This is upstream. Water will be coming from the upstream and then entering the petard tube. So once it enters the petard tube, the water will become stagnant at point 2. So the velocity will become the 0. So the kinetic energy of the water, because kinetic energy cannot be destroyed, but the fluid has got some kinetic energy here. Once it enters, it becomes stagnant. The kinetic energy cannot be destroyed, therefore it will get converted into the pressure head. That is why the water is rising in the petard tube. If you just write the Bernoulli's equation between 1 and 2, you will be able to calculate the V1. If you write the P2 by W plus V2 square by 2Z plus Z2. Z1 and Z2, they are at the same elevation, right? It can be cancelled. They are at the same height. But V2 is 0. Why V2 is 0? It is a stagnation point. The fluid has become stagnant. Stagnant means coming to halt. Once the liquid water enters this petard tube, at the tip of the petard tube, the water becomes stagnant. So see that the tip is facing the water coming from the upstream. A narrow hole will be there, a tiny hole. Once the water enters into the tiny tip of the petard tube, which is facing the water coming from the upstream, the water becomes stagnant. So the kinetic energy cannot be destroyed. So the kinetic energy of the water coming from the upstream will get converted into the pressure head. That is why water is rising in the petard tube. It is a free, it is a open to atmosphere only. Now V2 is 0. Therefore, V1 square by 2G is equal to P2 by W minus P1 by W. What is the P1 by W? If you just take this height as Y, what is P2 by W? Pressure head here, P2 by W. Here and here same, H plus Y minus, what is the P1 by W here? This depth, okay, minus Y. Therefore, V1 is equal to root 2G H. H is the, by what height the water is rising in the petard tube as compared to the outside free surface. That is a free surface. But to account for the little loss of energy, we may keep one coefficient of velocity CV. CV is called as coefficient of velocity. coefficient of velocity of pitot tube. That will be around 0.98, you can take 0.97 or 0.98 to account for the losses. So that is the velocity of the water. V1 is the velocity of the water coming from the upstream. No, here. P1 by W will be the Y. P2 by W will be the H plus Y. The principle here is the kinetic energy of the water coming from the upstream get converted to the pressure head. That is why water is rising in the pitot tube. Same thing can be used for measuring the velocity of oil flowing inside a pipe. Sometimes pitot tube can also be used like this. The water may be coming from here like this, and there is some manometric liquid levels. A U-tube manometer can be connecting between. This is the stagnation point. Is the water, some oil in pipeline, oil in pipe flowing. You want to calculate the velocity of this water here. Okay, now the difference in mercury like manometric liquid levels. This is a U-tube manometer, some manometer, and flowing pipe will be, oil may be having this specific gravity, yes. So when the oil enters this pitot tube, this is a pitot tube, L-shaped bent tube, it becomes stagnant. So all that kinetic energy of the oil at location 1 gets transformed into the pressure energy. That is why this limb is, this pressure here is more than the pressure here. So the difference in pressure heads between 1 and 2 will give the velocity head there. Here also V1 can be written as CV into root 2 GH, where that H could be given as X into so to measure the, this is the, to measure the velocity of oil flowing in a pipe. To measure the velocity of oil flowing in pipe, it can be used. In fact, the same pitot tube can also be used to measure the velocity of the aircrafts. Generally, that pitot tube is called as the Prandtl pitot tube. An aircraft will be moving, then aircraft. There they keep a small probe here. So the velocity of the air entering the pitot tube is nothing but the velocity of the aircraft, right? So by measuring we are converting the kinetic energy of the air entering into the pressure head by using this pitot tube. This is called as the Prandtl pitot tube. This is a famously known as Prandtl pitot tube, which is used to measure the velocity of the aircrafts. The principle is the air entering the pitot tube will be the velocity with which air enters the pitot tube will be the same as the velocity of the aircraft. So the air entering the pitot tube is made stagnant. This is the stagnation point. Once the air enters the pitot tube, it becomes stagnant, and the kinetic energy of the air gets converted into the pressure head. By measuring that pressure head of air, we can calculate what is the velocity of the air entering the pitot tube. Air enters here. This is a pitot tube. Air becomes stagnant here. So once the air becomes stagnant, the kinetic energy of the air gets transformed into the pressure energy. That is indicated as the difference in manometric liquid levels. Manometric liquid levels. By noting this manometric liquid levels, we can calculate what is the velocity of the air entering the petard tube, which is same as the velocity of the aircraft. This instrument is called as the Prandtl petard tube. So, petard tube is basically meant for measuring the velocity of the flowing fluids. Again, there is one more instrument called as an orifice meter. Orifice meter is also meant for measuring the discharge. Orifice meter will be it is connected, if this is the pipe, there is a sharp orifice plate is nothing but a sharp edged plate. When the water enters, this will get converged here. A narrow sharp edge, this will get converged, and that location where the area of the jet will become minimum, this point is called as the vena contracta. Orifice plate is nothing but a sharp edged plate having a narrow hole. So when the water or the any liquid enters through this passes through that orifice plate, that gets converged and again becomes diverged. By taking the pressure difference at the upstream and at this vena contracta, you will be able to calculate the discharge of the liquid. Orifice plate, supposing a fluid is flowing inside a pipe, they will connect the orifice plate like this. As the liquid enters, orifice is nothing but a hole, a small hole, when a small thickness of the plate will be there, a sharp edged hole. So as the water enters, it will become converging and then again gets diverged. The area of the minimum area of the jet is considered. That location is called as the vena contracta. By measuring the pressure difference between one and that at that location called vena contracta, we can measure the discharge of the water. Formula is same like venturi meter, but only thing is the coefficient of discharge for the orifice meter will be around 0.63. Orifice plate is a thin plate having a hole at the center of the plate. When the plate is located in the pipeline, by taking the pressure tappings in the upstream and at that location, P1 and P2, that will enable us to calculate the discharge of the water. Generally, that pressure tapping 2 is taken at that location where the area of the jet will be the minimum. That is called as the vena contracta. Okay. See, look at this. I will solve some problems on this fluid dynamics. The velocity of water flow from a tap of 12 mm diameter. There is a tap, 12 mm diameter, is 8 meters per second. What is the diameter of the jet at 1.5 meters from the tap when the flow is the tap is upwards? What is the direction? What is the from the tap and the flow is vertically upwards? The tap is like this and the flow is upwards. Here the diameter is 12 mm. Velocity V1 is 8 meters per second. It is going up at 1.5 meters. Okay. As the jet is going up, velocity keeps decreasing. That means area must be increasing. Jet will diverge like this because why? Velocity keeps decreasing. Q is equal to area into velocity. As the velocity gets reduced, area will increase. at a height of 1.5 meters from the tap. This is a tap, right? Exit of the tap. What is the diameter here? D2. This is D1. Okay. First, the pressure P1 at the location 1 and 2, it is same because it is open jet. Since open jet, P1 is equal to P2 is equal to P atmosphere, we can take. Atmosphere, open jet only this is. It is a tap. It is open jet, free jet. This is also called as a free jet. Open jet or free jet. So P1 is equal to P2. Z1 is equal to 0. Z2 is equal to 1.5 meters. We can take here as a datum. Datum we can take anywhere. For writing the Bernoulli's equation, see, for writing the Bernoulli's equation, some clues we have to keep in mind. The clues, these are the clues. Generally, Bernoulli's equation will be written between two locations, between 2 points. Wisely, we have to select those points wisely. Either we can select both the points or at least one location open to the atmosphere. Then what is the advantage? If you select at least one point to open to the atmosphere, you are automatically aware of the atmospheric pressure. What is the standard atmospheric pressure? If mentioned in the problem, take it. Otherwise, take it as 101 kilopascal. So that way, the number of unknowns in the equation can be minimized. Bernoulli's equation may be written between two locations. At least one of those locations, if you just consider open to the atmosphere, that pressure you are indirectly knowing it. Because when it is open to the atmosphere, we can write the atmospheric pressure. See, here both the locations 1 and 2 are open to the atmosphere. I know both are P atmosphere because it is a free jet. Jet is going up, free jet. And P1 is equal to P2. What is V1 there? Velocity 8 meters per second. Now let us calculate V2. P1 by W, V1 square by 2G plus Z1. Bernoulli's equation I am writing. P1 is equal to P2. We can cancel that. Z1 is 0. V1 will be 8 square by 2 into 9.81. G is 9.81 we may take. Sometimes in the examination you may specifically take G as 10 for simplification. V2 we do not know. Z2 will be 1.5 meters, from which we can easily calculate what is the velocity of the jet at this location. What is this velocity? We can calculate. Now I know the velocity V1. We could write the continuity equation. A1 V1 is equal to A2 V2. Continuity equation pi by 4 D1 square into V1. D1 I know, that is 12 mm diameter. D2 is asking pi by 4 D2 square into velocity V2. This velocity V2 we may substitute here. Pi by 4 can be cancelled both sides, and we may calculate what is the diameter D2 of the jet at this location. After flowing a height of 1.5 meters, what is the diameter we can obtain. So I have used only two equations. One is Bernoulli's equation and other is the continuity equation. This is the continuity equation. AV is constant. We got the diameter D2. It is a free jet. Therefore, free jet. Free jet means throughout the pressure is same, that is atmosphere. So, a very useful question. Now, this is one of the question asked in GATE only. Prandtl pitot tube. I already mentioned Prandtl pitot tube is meant for measuring the velocities of the aircrafts usually. Just take 1 minute break. Hello students, welcome back to the class. Now this is a problem on the Prandtl pitot tube. Look at the problem there. Prandtl pitot tube was used to measure the velocity of a fluid of specific gravity S1. Okay, the flowing fluid specific gravity is S1. The differential manometer with a fluid of specific gravity S2 is connected to the pitot tube, recorded a level difference as h. The velocity of the V is given by, very simple question. Velocity V is given by square root of 2g into h into S2 by S1 minus 1. Answer is B. I already explained this. So as the oil enters here, it has got the velocity, it has got some velocity V. But once it enters here, it becomes stagnant. This is the stagnant point. So all that kinetic energy will get transformed into the pressure energy. That is where this limb level, the pressure here is more. The kinetic energy gets transformed into the pressure energy. That is why there is a difference in limb levels. So by noting down the difference in limb levels, we can get the velocity. This is the formula. Look at this. The velocity at the exit of the pipeline as shown in the below figure is. I already said, whenever we are writing the Bernoulli's equation, two points will be there. Either you select one of them or at least one of them, or both the points, preferably open to the atmosphere. So this is the free surface. So this point and this point, we can write it as the Bernoulli's equation, because both are open to the atmosphere. And moreover, one more thing I would like to tell. When you write the Bernoulli's equation, another clue is preferably take the one point in a large surface. Like this. What is the advantage if you take in a large surface? There the velocity becomes negligibly small. So certain clues we have to follow while for choosing the points for writing the Bernoulli's. One clue is either one point or both the points must be open to the atmosphere, number one. Another important thing is preferably take the one point in a large surface, large tank like this, so that there the velocity becomes 0. V1 is 0 here, plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2. Z2 itself we can take it as the, here itself as the arbitrary datum. Z2 is 0 and P1 and P2 both are open to the atmosphere, can be cancelled. V1 is 0. Since why V1 is 0? Large surface in tank. Since large surface in tank, V1 is 0. V2 is equal to root 2G into Z1. Root of 2 into 9.81. What is the Z1 there? Height elevation 5 meters, right? So 2 into 10, 20, 5 into 20, 100. It will be nearer to the 9.9. Answer is A. This is open to atmosphere. This is also open to atmosphere. Jet here, that the jet of the water issuing will be 9.9 here. This velocity V2 will be 9. A tube is used, as shown in the figure, as a siphon. Siphon is a very commonly used a hydraulic, not a device, it's a pipeline. Suppose it is like this. I can explain the siphon like this. Suppose that we have a water resource, some river is there. There is a pipe passage. Your field may be at that your field or the like a where it need to be irrigated. So then you can take a pipeline running. You don't require any pump. Just run a pipe from that water resource into that field, but the level of the water in the resource must be at a higher elevation than the field. Automatically the air can be discharged, water can be discharged. We don't require any pump. Only condition required is the level of the water in the river must be more than the level of the field. Field means your agricultural land where water need to be irrigated, right? So just run a pipe, automatically water keeps discharging. This is called as the summit of the pipe. This location is called as the summit of the siphon. So it is a siphon. See, you are discharging the water from this point to this point. So this is a free surface. This is a free surface, right? Now, what he has asked is discharge an oil of specific gravity 0.8 from a large open vessel into a drain at atmospheric pressure. The velocity of the oil through the siphon is. See, this velocity of the oil is asking. So this velocity is same because area of cross section is same. Velocity Vc is equal to velocity Vb. So this velocity we need to calculate. So what points we need to take the Bernoulli's equation? One point preferably I take open to the atmosphere, and another point C also I taken to here, which is also open to the atmosphere. It is a large surface, means V1 is equal to 0. Here atmospheric pressure, here also atmospheric pressure. Now let us calculate write the Bernoulli's equation. Bernoulli's equation between 1 and 2. I have selected both the points open to the atmosphere, and I preferably selected this point because it is a large. He has used the word, see that, discharge in open vessel, large open vessel. That means here V1 is automatically become 0. So P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W, V2 square by 2G plus Z2. Z2 will be, you can take here as the datum. That means Z2 will become 0. When you take this datum, you can select anywhere. For writing the Bernoulli's equation, you may select the datum anywhere. Means from that location onwards, Z will be measured. I have selected the datum here. Z2 is equal to 0. And V1 is 0 because it is a large surface. V1 is 0. P1 is equal to P2 because both are open to the atmosphere. Therefore, V2 is equal to root 2G into Z1. 2 into 9.81 into what is Z1, let us select with reference to this datum. Z1 is here, right? So 4 plus 1.5, 6.5. This is the answer. 20, you can easily get the answer there. 2 into 9.81 into 6.5 under root. You will get one of those answers. 20. Answer will be 10.4. It should be definitely more than 10 because that value is more than 100. 10.4. Okay, answer will be D. Without calculation, I can tell. It is a previous gate question only. A mercury manometer is attached to a section of the pipe like this. Mercury levels are indicated when there is no water. There is no water flowing in the pipe. When the water starts flowing through the pipe like this continuously at constant rate in the direction of the arrow, there is a flow happening. Water flow. Then the level of the mercury at B. Will it go down? Will it go up? Or will it same as this? We have to understand. That could be understood like this. When the water is flowing is happening here, the area is lesser. From here to here, area is decreasing. Area is decreasing means velocity must increase. When the velocity increases from here, area is decreasing. That means velocity must increase. When the velocity increases, because P by W plus V square by 2G plus Z is equal to constant. But there is a same elevation, right? All are at the same elevation. So Z doesn't matter. So when the velocity area decreasing, AV is equal to constant. When the area decreases, velocity increase. When the velocity increase, pressure must decrease. That means here the pressure is lesser than this. But when you come to here, pressure is lesser. But when you come to here, pressure will be, here the pressure is lesser. Again the area is increasing, velocity decrease, pressure will increase. That means here the pressure is lesser, therefore the level of the B, the level of the mercury will move up. Level of the mercury will move up and this will come down. Okay. What happens here? The pressure at this location is lesser than the pressure at this location. That is why level of the mercury here at B will move up. Try to understand. As the area reduces, velocity will increase. When the velocity increases, pressure will decrease. From here to here, area is increasing. That means velocity will decrease. When the velocity decreases, pressure will increase. That means here at this location, pressure is more than at this location. PA is greater than Pb. Therefore, this level of the mercury will move up. This will come down, okay, this level. The level of mercury will move up, will go up. That is the answer. It is also a gate question, previous gate question. Water flows through a vertical contraction from a pipe of diameter d here to another diameter d by 2. This is d by 2, this is d. The flow velocity at the inlet to the contraction is 2 meters per second here. Here it is inlet to the contraction is 2 meters per second. And the pressure is here, if you just take this as section 1, pressure is 200 kilonewton per meter square. If the height of the contraction is 2 meters, then the pressure at the exit of the contraction here. If you just take this as 1, this section as 2, what is P2 is asking. Just write the Bernoulli and continuity, you will get the equation. What is the velocity here? Water flows through a vertical contraction to another pipe of d by 2, right? A1 V1 is equal to A2 V2. Pi by 4 d square into V1 is equal to pi by 4 d by 2 whole square into V2. Now I could write this V2 in terms of V1, right? So pi by 4, pi by d square will get cancelled. V2 will be 4V1. We got it from the continuity equation. This is continuity. From the continuity equation, AV is constant, mass flow rate is constant, therefore area into velocity discharge is constant. Now if you write the Bernoulli's equation, P1 by W plus V1 square by 2G plus Z1 plus Z2. Okay. Now Z1 is equal to 0 we can take. Z1 is equal to 0. Z2 will be 2 meters. Now what is P1 by W? 200. It is water only. 200 divided by 9.81. What is V1? V1 square by at the inlet to know V1 I know. V1 is 2 meters per second. V1 is 2 meters. V1 square by 2G. Z1 is 0. P2 we do not know, divided by 9.81. V2 will be 4V1 whole square by 2G plus Z2 will be 2 meters. Put V1 as 2 meters per second. He has given this. He has given the velocity at the entry here. Now we will get the pressure in kilopascal or kilonewton per meter square. Elevation we have to set, datum we have to wisely select. Z1 is equal to 0, Z2 will be 2 meters. So very good question. This is a gate question only. Understand? I have written the continuity equation between 1 and 2. I got the velocity V2 in terms of V1. V1 is already given, 2 meters per second he has given. Then I write the Bernoulli's equation between 1 and 2. It is a previous gate question. He has given the P1. Because I have taken the datum here, Z1 is equal to 0. Z2 will be 2 meters height and the P1 has been given. I can calculate the P2. V1 is 2 meters per second. Substitute that V1 here. And then very important precaution in the for writing the Bernoulli's equation is very important precaution. P by W. What units of P we have to keep means always keep the pressure only in kilopascal, kPa only, that too absolute only as far as possible. And W units, for the W we have to keep the units always the 9.81 kilonewton per meter cube. We should always, as long as if you keep it in kilopascal, W must be kept in kilonewton per meter cube. We remember the water specific weight as 9.81 kilonewton per meter cube. So that this ratio will become meters. Pressure head, this is called pressure head, which should have the units of meter. So this is a very good question which is also given in GATE only. Air flows through a venturi and into the atmosphere. Air is flowing like this into a venturi and into the atmosphere. This is the atmosphere. Here the pressure is atmospheric pressure. Air density is rho, atmospheric pressure is Pa, throat diameter is dt. This throat diameter is dt at the throat. This is the throat section. Exit diameter is d here. And the exit velocity is u. Air is leaving the venturimeter with a velocity u. Throat is connected to a cylinder. Here there is a cylinder containing a frictionless piston. This is a piston. Throat is connected to a cylinder containing attached to a spring. This piston is attached to a spring. Look at this. There is a spring here. Spring constant is K. The bottom surface of the piston here, the piston is exposed to the atmospheric pressure. So what is the pressure acting on the bottom side of the piston is atmospheric pressure. Due to the flow, piston moves by the distance x. Assuming incompressible frictionless flow, x is. It's a very good question. Very good question this is. Now this question can be solved by writing three equations. One is continuity equation, conservation of mass. Second thing is Bernoulli's equation, that is a conservation of energy. Third thing is the force balance equation for this piston. The piston is inside a cylinder, right? First let me write the conservation of mass, that is continuity equation. So when the flow is happening between these two locations, I write, okay, pi by 4 area into velocity at the throat, area at the exit into velocity at the exit u, from which velocity at the throat can be calculated, right? That will become d square by dt square into u. This Vt is the velocity at the throat. What is Vt? Velocity at the throat here. Here velocity at the throat, we got it by writing that between here and here I write the continuity equation. Area into velocity here should be equal to the area into velocity here. Now I write the Bernoulli's equation between throat. Between throat and exit, I write Bernoulli's equation. How to write the Bernoulli's equation? Pressure at the throat divided by rho g, P by W, plus velocity at the throat square divided by 2g, elevation at the throat, it should be equal to the, what is the pressure at the exit? Atmospheric pressure here. Here it is atmospheric pressure given, divided by rho g, u square by 2g, plus Z at the exit. But the Z at the exit is same at the Z at the throat. Elevation is same. Look at this. Here and here elevations are same. Now pressure at the throat I could write like this. Pressure, let's write that. Now pressure, now see this. Pressure at the velocity, U area is increasing, right? As the area is increasing, velocity must be decreasing. When the velocity decreases, velocity is decreasing. But because area is increasing, velocity is decreasing. When the velocity decreases, pressure must increase. Here the pressure is more means here the pressure is lesser. When the pressure is lesser, Pa by rho g, Pa minus Pt by rho g is equal to here throat pressure is lesser than the atmospheric pressure. Pa is equal to V1 by Vt square minus U square by 2g. But Vt square we could write it as d square by d square into U whole square here, right? That means already you will get d to the power of 4. Now, if you write the force balance, for this, force balance for piston, here I am writing, there is a piston. From the upside, piston area is also given, ds square, this is a piston. From the upside, what is the pressure coming? Pt. From the bottom side, what is the pressure acting? Pa. Pa is more or Pt is more? Pa is more than the Pt, because I already said there. Area is increasing, velocity is decreasing, means pressure must be increasing. Here the pressure at the throat is lesser than the atmospheric. That means, if you write the force, that means this because of this pressure, piston tend to move up, but there is a spring. There is a spring which is trying to, because when the piston is moving up, the spring connected to below that, it will try to pull it down. That means spring force will be downwards. Spring force will be downwards. So on the piston, spring force will be downwards because spring is pulled up. When the spring is pulled up, because the pressure is more here, it will try to push the piston upwards. That means spring is pulled up, but the spring is trying to pull down the piston downwards. That means spring force is downwards. What is the spring force? K into X. So for the force balance, Pa minus Pt into pi by 4 ds square. Ds is the diameter of the piston, should be, that means the upward force should be equal to the K into X. Okay, K into X will be downwards, but Pa minus Pt into area will be the upwards. We can calculate the X here. Now Pa minus Pt by rho g we can substitute here, and Pa minus Pt by rho g pi into pi by 4 d square. This Vt could be replaced by square of this. That means d power 4 will be coming. Answer will be obviously d only. Without calculation I can say answer will be d without calculation. How can I tell? Because we have the power force only in the last option. Why you get a power force? Because when Vt square is there, you should get the power force here. D square by dt square, you will get the power 4 will get. So answer will be D. You can calculate this. X will be, K will come down, pi by 4 ds square, Pa minus Pt we can obtain from this formula. Rho g will come there, g will get cancelled. So you can easily tell that answer will be the D. Without calculation also you can. You don't get the power 4 in the diameter in the other options. See, we don't have to do the other options because power force will be there, because when you see the V2 square, you will get only to the power of 4 only in the last option. So by default option will be D. We don't have to do that. Gate questions will be like that. Gate questions will be like that. We can easily guess the most possible answer. We don't have to do completely. We don't have to waste time for complete. I can directly say this should be the answer because only it has got the power force. Other options has got only square. Why you get a power 4? Vt square is there, this ratio will get the power 4. So, very good question. So, totally we have to use the three equations: continuity equation, Bernoulli's equation between throat and exit, and the force balance. Force balance for this piston. So, in fact, whenever we are trying to solve a fluid dynamics problem, most of the fluid dynamics, 99%, you have to use the three conservation rules. In all these problems, you may observe two conservation rules I am compulsorily using: continuity equation and Bernoulli's equation, conservation of mass and conservation of energy. The third equation I am using like a force balance here or a manometry equation, but in majority of the fluid dynamics there will be the third equation you need to be used will be impulse momentum equation or conservation of momentum, which is a vector equation. As you are all aware, mass is a scalar, energy is a scalar, but force, impulse, momentum, they are vectors. So, the third conservation called conservation of the momentum or impulse momentum equation is a vectorial equation. Slightly complicated because we need to bother about the directions. Here we are never bothering about the directions because mass is a scalar quantity, energy is a scalar quantity. Very easy to write both continuity equation and energy equation, that is Bernoulli's equation, both are scalar. But the third equation called impulse momentum equation is slightly complicated because we have to bother about the direction. Okay. So, with this I will close today and I will solve some more problems in the tomorrow's class about the fluid dynamics. Fluid dynamics is a main central area of the FM where the lot of questions can be expected in kinematics and also in the dynamics. And I expect you to answer come with the doubts. In fact, my number also is available 98494-10269. You may interact with me. This is my number 98494-10269. My name is Sekhar, one of the senior most faculty in GATE across India. 98494-10269. You may interact or you may call me and interact with me also. Okay. Wish you best of luck. Good night.